Alright, we're going to talk about confidence intervals about a proportion. So now we're going to try and guess at proportions using the stuff that we've been talking about with confidence intervals. So our warm-ups. Suppose a confidence interval for some proportion P is 0.58, 0.92. What is the point estimate? Well, the point estimate is the middle. So to find the middle, we do 0.58 plus 0.92 divided by 2, and that gives us 0.75. Then what is the margin of error? Well, it's whatever we can add to 0.75 to get 0.92, whatever we can subtract from 0.75 to get 0.58, or the distance here, if we subtract them, 0.34 and divide it by 2. Either way, we get the margin of error of 0.17. It's the distance from the point estimate to the upper or to the lower. So we could have done 0.92 minus 0.75, 0.75 minus 0.58, or subtract the two boundaries of our confidence interval and then divide that by 2. We get 0.17. So that's our margin of error. What conditions need to be met to be able to say that a sampling distribution of a proportion is normally distributed are tens. N times p hat has to be greater than or equal to 10, and n times 1 minus p hat has to be greater than or equal to 10. And it's p hat because we don't have p. We're trying to guess at what the proportion is, the true proportion is. What conditions need to be met to be able to find the mean and standard deviation for a sampling distribution of a proportion? The 10% rule, that at least we are less than 10% of the total population, whatever that is. And we don't have a situation here, so we can't apply to that, but it's just our 10% rule. And what is the general formula for a confidence interval? It's our point estimate, or our statistic, and that's what our formula sheet says, plus or minus the critical value times the standard deviation of the statistic, and this part is our margin of error. And now we're going to get into how we find those parts. So there are 4 things that we're going to do in 8.2. The first one is check the conditions to be able to create a confidence interval for a proportion. So it's very similar to what we did before. Then we determine critical values for confidence intervals for a proportion. So we have our critical value here. Well, we didn't really talk too much about it, and we have to find that. Construct and interpret a confidence interval for a proportion. Find the sample size needed to be able to estimate within a certain margin of error. Those are the 4 things. These are the 2 types of problems that you have to be able to do, and these need to be done every problem that you do. So really they all go together very, very, very well. So here are the conditions needed to make a confidence interval about a proportion. So the data has to come from a random sample and needs to be random. If it's not random, it doesn't count. And then the other conditions that we've already been doing. The sample size is less than 10% of the population, and n times p hat has to be greater than or equal to 10, and n times 1 minus p hat has to be greater than or equal to 10. Here's our confidence interval. So a statistic plus or minus the critical value times the standard deviation of the statistic. Well, for a proportion, the statistic is p hat. The critical value we're going to call z asterisk or z star, a little bit easier to say, and then standard deviation of a proportion is this formula, which we've already been using. And why are we using p hat instead of p? Because we're using p hat to guess at p. We don't know what the proportion actually is, the true proportion. We're using a point estimate, something from a sample to guess. And that is statistical inference. Taking a sample and using it to make a conclusion about a population. That's what we're doing, and that's what we're doing this whole semester. So that's the conditions need to make a confidence interval about a proportion. So there's only really one new one, and it being random really isn't that big of a deal. But it's something we need to keep in mind every time we do a problem. Determine critical values for confidence intervals for a proportion. Now we're going to do these by hand for the first problem, and then I'm going to show you how to do them on the calculator. Well, we're going to use the calculator anyways, but we're going to use the calculator completely for everything for finding a confidence interval on the second example. So here are our steps. 1, draw a normal curve and label everything. Label our mean, label our standard deviation. Subtract the level of confidence from 100 to find the unshaded area. We want confidence within 2 values and we want it centered. Divide the number from step 1 by 2. The area is split up into 2 tails of the curve. And then find the 2 boundaries of the shaded area using inverse normal function on your graphing calculator. So it's stuff that we've already done before, but we're just looking at it a little bit differently. So, for example, if we want a 95% confidence interval about a proportion, we want something that gives us a middle 95%. So our first step is to label our graph. So here's our middle 95% that's shaded. I have it labeled. So our second step is subtract our confidence level from 100. So we get 5%, and that 5%, that's step 3, divided by 2, means we have 2.5% in each tail. So these are called the tails. I think we've talked about that before. But we have 2.5% in each tail, and we have to think about that. So what we need to do is find the z-scores that give us this. Now, because this is symmetrical, we really only need to find one of them. So how do we find it? Well, it's inverse norm, and it's the area to the left. So the area to the left of z1 here is 0.025. Over here, the area to the left is 0.95 plus 0.025, so 0.975. These two are complements. They're always going to add up to 1. But if you notice, the numbers that we got are the same thing, just one's negative and one's positive. So our critical values are 1.96, negative 1.96, and 1.96, which is why we do plus or minus when we're using our formula, because we have 2 critical values. So those are our first 2 steps doing the problems. Now we actually have to do the problems. Actually, we have another example. Find the critical values for 90%. Well, we draw it out first, middle 90%. That means we have 5%. Oh, I'm skipping some steps. So 100 minus 90 is 10, so we have 10 in each tail combined. Divide that by 2, so we have 5% in each tail. Then, to find those 2 z-scores, we do inverse norm of 0.05 and 0.95, and we get negative 1.65 and 1.65. So those are our critical values, plus or minus 1.65. So because it's symmetrical, that's why we have plus or minus. And again, here is our confidence interval formula. If we just want the margin of error, well, it's just this part. And that's what this is talking about. So we have 2 different types of problems that we're going to deal with. One, the main problems where we're going to construct and interpret a confidence interval for a proportion. And we have the acronym PANIC for that. We'll talk about that in a second. Then we also have to find the sample size needed to be able to estimate within a certain margin of error. Suppose we want to be within 3%, how many from our sample do we need to take, or what sample size do we need? So we'll go over that in a second. But let's look at constructing a confidence interval. So PANIC. P is parameter. Write out and label the parameter we are trying to estimate. What P stands for? Not probability, but the proportion. And in this case, it's parameter proportion. Then we do our assumptions and conditions. We check the conditions are met to find a confidence interval about P. So the things that we talked about there. And name the test. Right now, we're always going to be naming the same thing. 1 proportion Z interval. It's 1 proportion, it's Z, and it's an interval. So it's pretty straightforward. I, interval, construct the confidence interval. This is where we actually physically put together the algebra to make it. We'll do it once where we put it together, and then I'll show you how to use the calculator. And then conclusion, interpret the interval. This is where we say what it means. So what we've already been doing, but now we're doing it with real problems. So let's look at that first. So students in an AP statistics class want to estimate the proportion of pennies in circulation that are more than 10 years old. To do this, they collect a random sample of 102 pennies. Overall, 57 of the 102 they collect are more than 10 years old. So we do our panic. So I'm not going to number the steps, but I have the letters for the steps. So P, what we're talking about, the parameter. Well, we want to know the true proportion of all pennies in circulation that are more than 10 years old. That's what we're looking at right now. And this is going to be helpful when we write our answer because we know exactly what we're talking about. The true proportion, or the proportion of all pennies. So we kind of have that in there twice. Then our assumptions and conditions. It's random, because it says it's random. Clearly 102 is less than 10% of all pennies in circulation, by a long shot. Then we do our n times p hat. Well, p hat we have to find still. We look at the number of pennies that we collected that are of the proportion we want. 57 out of 102 are more than 10 years old, and that's what we're looking for, more than 10 years old. So 57 over 102 is about 0.559. I rounded a little bit, and that's okay. So it's n times p hat, which gives us 57.02, and of course that is greater than 10. You need to multiply those two numbers out. Do not stop here. That is incorrect. You need to actually show me that they're greater than 10. Then we do n times 1 minus p hat. Well, 1 minus p hat is 0.441. So we multiply that, we get 44.99, which again is still much greater than 10. So all our conditions have been met to do a confidence interval. So these two are exactly the same as what we were doing before. The only new thing is that we have that it's random as well. Then we name the test. Real simple. It's a 1 proportion z interval. That's it. Done. Move on. Our interval. Alright, so now really what we're just doing is we're plugging numbers into this formula. P hat is 0.559. Z star, this is where we had to find our critical values. Our middle 95%. Now, it didn't say what confidence level we wanted. If it doesn't say, we're going to do the 95% confidence level, because that's most common. So middle 95%, so 1 minus that would give us 5. And then when we actually find the two tails, 5 divided by 2 is 2.5%. So 2.5% is what's in the two tails, so just like what we did up here, we do inverse norm, and really we only need to do it once, but inverse norm of 0.025 or 0.975, because that's what the area to the left of this value, we get plus or minus 1.96. So that's our z star. Then square root of 0.559 times 0.441 over 102. So we're just literally plugging in numbers. And when we plug those in, we get a lower bound of 0.463 and an upper bound of 0.655. So we have our interval. Then last, C, we need to interpret our conclusion. We are 95% confident. And again, we are 95% confident. That's not going to pop through. Sorry. 95% confident that the true proportion, and this was just copied right from P, right from up here. So I didn't have to think about it again. That's why it's important that we write it the first time. So we're 95% confident that the true proportion of all pennies in circulation that are more than 10 years old is between the numbers that we got based on our sample. And that's it. That's all we have to do. That's finding the confidence interval. Now, if we want to do it on the calculator, it's much easier. We still have to do the P, the A, the N. But when you get to I, you can skip all the calculations and have the calculator do it for you. So if we're using the 84, you go to Math, No, I lied. You go to Stat, and you go over to Tests, and we want one proportion z-interval. Exactly what we're writing for the n, name the test. Now, what do they want to know? They don't even want to know p hat. They're going to find p hat for you. You just have to type in x, the number of successes, which we had 57 successes out of 102. And then the level of confidence, which is going to be standard of 0.95, so we're just going to keep it there and calculate. There's our interval, 0.462 and 0.655. That's exactly what we got, just rounded a little bit. It also found our p hat, which was nice. P hat, and it found n, we typed that in, so we didn't really need that. If you're using the Inspire, same type of thing, menu, statistics, and it's under confidence intervals, oddly enough. The one proportion z interval, same type of thing, 57 out of 102. It actually finds a margin of error as well, so it gives us a little bit more, but we should be able to find that anyways. So that's what we're going to do from now on instead of using the formula. Now, the other type of problem that we have to look at is finding the sample sizes needed to be able to estimate within a certain margin of error. So we need to find the critical value for the given confidence interval, just like what we did over here. Find the point estimate for the proportion, and if we don't have one, we use 0.5. Because 0.5, if we use 0.5, it'll make p hat and 1 minus p hat the biggest value possible, and it'll give us the biggest estimate, so that we're not overestimating, we'd be underestimating, but we'd rather underestimate than overestimate. So again, if we don't have the point estimate, if they don't give us some kind of guess, we use 0.5. Substitute these values in the margin of error formula. It's just this part. The z star times p hat times 1 minus p hat over n square root, solve for n, we're going to use the calculator to do that, and always round up the n value because we need at least that many. So again, a national opinion poll found that 44% of all American adults agree that parents should be given vouchers that are good for education at any public or private school of their choice. The result was based on a small sample. How large an SRS is required to obtain a margin of error of 0.03, that is plus or minus 3%, in a 99% confidence interval. So we want to know the sample size to be able to guess within 0.3 or within 3%. So first we have to find our critical value. So just like what we did before, we want 99% confidence, so it's 100 minus 99, which is 1, divided by 2, which is 0.5%, or if we turn into a decimal, is 0.005. So we do inverse norm of 0.005, and again, really remember it's plus or minus 2.58, because we could have done it for that as well, the other side, if we would have drawn out our curve. I don't think we need to. Our p hat is 0.44. That's our point estimate. That's what they told us. They told us that they already did a sample and they got 44%. So we plugged in our numbers. 0.03 equals 2.58 times the square root of 0.44. 1 minus 0.44 is 0.56 over the square root of n, and we solve for n. Now, we can solve using our calculator a lot easier than trying to do this by hand. So let's look at the 84 first. Now their solver is a little bit weird on this. So under math, and it's on the bottom, solver. And so the equation has to be equal to 0. So it's 2.58 times the square root of 0.44 times 0.56 over x minus 0.03. So if you noticed from here, all I did was subtract 0.03 from both sides to set it equal to 0. And so when you hit enter, it brings you something here. Now you need to put in a value here. I don't know why. Put in 2, put in anything, and then hit alpha. And if you hit enter, you can see that it actually does the solve part. And it gets us 1822.37. So that's the sample size that we need. So 1822.37, so we need a sample of 1823 because we have to round up. Again, using the calculator to solve for us. If we're using the Inspire, it's a little bit easier and it makes things look a little bit nicer. But under algebra, numerical solve, and then we type in our equation. We don't have to set it equal to 0. So 0.3 equals 2.58 times the square root, get our fraction here, 0.44 times 0.56 over x, and then we want to say we want to solve for x. And we get the same number. And then the nice thing about really both of these, I can arrow up, hit enter, and then just plug in new numbers when a new problem comes up. The 84, this is still solved in here, or saved in here, so we just have to change the numbers. So we'll do that for the next problem. Alright, so let's do another problem of both confidence interval and the sample size, but we're going to use the calculator for it. So in her first grade social studies class, Jordan learned that 70% of Earth's surface was covered in water. She wondered if this was really true and asked her dad for help. To investigate, he tossed an inflatable globe to her 50 times. Being careful to spin the globe each time when she caught it, he recorded where her right index finger was pointing. In 50 tosses, her finger was pointing to water 33 times. Construct and interpret a 95% confidence interval of the proportion of Earth's surface that is covered in water. This is kind of a lame experiment, but it still gets our point across. So P, remember we're doing our panic. P, the true proportion of Earth's surface covered by water is what we're trying to find out. That's our parameter. Then, is it random? Yeah, it was randomly tossed. Pretty lamely, but it was randomly tossed. And clearly 50 tosses is less than 10% of all possible tosses. Kind of a stretch, but that's what we want. So P hat was 33 out of 50, because that's how many times her finger landed on water. So 0.66 is P hat. So we plug it into our tens. We get 33 is greater than 10 and 17 greater than 10, so our assumptions are good, so we can continue. It is a one proportion Z interval. Right now, that's all we're doing. So for N, name the test. You simply name it. Now, we're going to use the calculator to find our interval without doing all those calculations. So, stat, test, and if we go from the bottom, it might be a little bit quicker. It's letter A. So it was 33 out of 50, and let's see what percent we wanted to deal with. 95% still, so calculate, and there's our P hat, which we already found, and our confidence interval. We can do the same thing here on the Inspire menu. Oops. Statistics, confidence intervals, one proportion Z interval. It was 33 out of 50, 95%. There you go. Our lower limit, our upper limit, our P hat, our margin of error if we wanted that. But we get this interval. So we just interpret it. We are 95% confident that the true proportion of Earth's surface covered in water, right from here, is between 0.5287 and 0.7913 based on our sample. Done. We did our panic. Last example, suppose that we wanted to estimate the true proportion of students at our school who have tattoos with 98% confidence and a margin of error no more than 0.1. So first, we need to find our critical value. 98%, so we do 100 minus 98, get 2% on both tails combined, divided by 1, so we have 1% or 0.01 in each tail, inverse norm, and we get 2.32. Now remember, I don't really want to see this, but I'm showing us how to find it. So our critical value is 2.32, p hat is 0.50 since no given estimate. We don't have any prior estimate, we're just kind of taking a guess. So we plug into our formula. Remember, it is p hat equals z star times square root of p hat times 1 minus p hat over n. So we plug in 0.5 for p hat, we plug in 2.32 for z star, and p hat, not p hat equals the margin of error. And our margin of error is always going to be, well, it says margin of error 0.1, so we want to be within 10%. So this is our equation. So again, if we're using our calculator, we're using the 83, we go to our solver, we go back, and all that same stuff's here, we just have to kind of change some of our numbers. So instead of 5.8, it's 2.32, our p hats are 5.0, and 1 minus p hat is 5.0, and our margin of error is 10. We hit enter, we hit alpha, enter, and we got a sample size of 134.56 is what we need. We can do the same thing with this. Nice thing about this, just arrow up, copy, again, just change the numbers. And we get the same number. So n equals 134.56. Well, we need to round up. We would need a sample of 135 students to be able to estimate with 98% confidence within 10% how many students in the school have a tattoo. So we're not going to do these two examples in class, but obviously if you're watching this, you went ahead and looked at them.